Welcome to this explainer. Okay, today we're settling in for a friendly, really focused study session. If you're learning the fundamentals of database management systems, DBMS, you're in the exact right place. We're going to take all those, well, seemingly intimidating foundational concepts like how data is structured, how it's hidden away, and how it's physically mapped out on computers, and we are going to break them down completely. By the end of this, you'll have a crystal clear study guide to just absolutely ace your understanding of database architecture. Okay, let's dive right into this. Here's our roadmap so you know exactly where we're headed. First, we're going to peel back the layers of data abstraction. Then we'll tackle a classic exam topic, schema versus data instance. And finally, we'll map out defining database architectures, from simple single and two-tier systems all the way up to three-tier and n-tier models. So to kick things off, let's think about a really fundamental problem. Databases are, by their very nature, incredibly messy. They're made up of massive, complex data structures packed onto hardware. But, as users, we definitely don't want to see all that. We want a clean, cute, easy way to interact with our information, right? So how exactly do we make incredibly complex data easy and friendly to use for everyday people? Well, the answer is data abstraction. Think of abstraction kind of like a protective shield. Developers use this process to deliberately hide the internal, completely irrelevant complex data structures from the user. Like, when you check out of an online store, you don't need to know how this server is allocating bytes on a hard drive, do you? No way. Data abstraction keeps those scary technical details safely hidden away behind the scenes so you can just focus on what you actually need to do. To pull this off, databases use a three-level architecture. It's honestly a lot like peeling an onion. We start from the outside, where the user sits, and go all the way down to the core, where the data actually physically lives. Those three steps are Step 1, the view level at the top, Step 2, the logical level right in the middle, and Step 3, the physical level at the very bottom. Let's look closer at each one. Let's start right at the top, the view level. Now, sometimes you'll hear this called the external level. This is the top layer where you, the end user, interact with a clean graphical user interface, or GUI. At this level, you can view your desired data without ever seeing the messy database schema details. The user is just blissfully unaware of what data is actually stored behind the screen, or, how it even got there. Stepping down one layer, we hit the logical or conceptual level. This is the middle ground, and actually, this is typically where database programmers and administrators live. They aren't really worrying about the physical hardware. Instead, they define exactly what data is stored and how it all relates. This whole level is about defining tables, establishing relationships amongst the data, and setting up crucial things like constraints and security. Finally, we get down to the absolute lowest layer, the physical or internal level. This describes how the data is actually stored. We're talking about the complex data structures, allocating space on storage devices, and packing data into actual storage blocks in memory, measured out in bytes, gigabytes, and terabytes. It's the gritty, literal reality of where the digital information physically sits on the hardware. Now, navigating all these levels requires a solid blueprint, which brings us to a really critical study focus, the schema. A DBMS schema refers to the unchanging structural view, or the permanent design, of the database. It is literally the blueprint. And just like our three levels of abstraction we just talked about, there are three corresponding types of schemas: the physical schema for the storage blocks, the logical schema for programmers structuring records, and the view schema for end-user interaction. And this brilliantly illustrates what a schema actually looks like in practice. Here we have a clean structural view mapping out the relationship between a course, a student, and a section table. But notice what's missing. There is absolutely zero actual data here. There are no student names, no course grades. It is perfectly empty. It's just the logical blueprint defining the structure of those tables and exactly how they connect to each other. This naturally leads us to one of the most important contrasts you absolutely need to grasp for your exams: schema versus instance. As we just saw, the schema is the permanent blueprint, the design. But an instance refers to a snapshot of the data stored in the database at one exact moment in time. The schema is long-term, it rarely changes, while an instance is just a temporary snapshot of the data values right then and there. To make this super concrete, just imagine a single student table. Let's say today that table has 100 records in it. So right now, the instance of our database is 100 records. But tomorrow, a brand new semester starts and we add another 100 students, bringing our total to 200. The underlying design, the schema, stayed exactly the same,
But because we added data, the instance changed. So remember, the instance is always evolving over time as data is added or deleted.
Okay, let's move on and see how this all builds into the broader world of database architecture. We've talked a lot about how data is abstractly organized, but database architecture refers to the conceptual structure and the logical organization of the computer system itself. It describes how the database connects, the applications used to access it, and where the users physically sit in relation to the whole setup. Crucially, the type of architecture depends entirely on the computer system the database program is running on. And based on that design, we can divide DBMS architecture into four main categories: one-tier, two-tier, three-tier, and n-tier systems. Let's break each of these down, starting with the absolute simplest. First up is the one-tier or single-tier architecture. This keeps absolutely everything: the user interface, the middleware, and the backend file server huddled together in one single place: your client computer. If you're learning DBMS and you, say, install MySQL directly onto your personal laptop to store and manipulate data locally, you are using a one-tier architecture. It's a totally direct, simple, and all-in-one local setup. But what happens when we need to separate things? That's where we contrast one-tier with two-tier architecture. While one-tier is an all-in-one local setup, two tiers splits the workload. The application program, like a nice visual GUI, runs on your client machine, but the actual database lives remotely on a completely separate server. To make them talk to each other, we use an API layer, like Open Database Connectivity or ODBC, to translate between your client app and that remote database server. Now, as the internet grew, we needed something even more robust, which gave us three-tier architecture. This is the backbone of most web applications today. This model has three distinct layers. First, the user or presentation tier, which is where you interact with the app. Second, an application or middle tier, which acts as an intermediate server running the logic programs. And third, the database or data tier, where the actual data and query languages reside. And the absolute beauty of this three-tier system is its independence. In this setup, the end user has absolutely no idea the database even exists, and the database has no idea the user exists. They only ever talk to that application server sitting in the middle. Because of this, each neat little layer can be operated, managed, and upgraded entirely individually without breaking the whole system. It's brilliant. It provides incredible strength and flexibility for large distributed networks. Now, what's really interesting here is that we can push that separation even further with n-tier architecture. N-tier involves physically dividing an application into three or more distinct layers, usually a presentation layer, a business logic layer, and a data access layer. The communication here is strictly linear. Information must pass straight through that middle logic layer to get from the user interface down to the database. No skipping steps. Before we wrap, let's clarify a point that often confuses a lot of students: N-tier versus MVC, or Model View Controller. While they sound kind of similar, N-tier is a physical separation of the application's parts, and communication is linear. MVC, on the other hand, is a conceptual framework where the interaction is actually triangular. In MVC, the controller accesses both the view and the model can also crosstalk and access the view. They aren't mutually exclusive, though. You can actually use the MVC framework right within the presentation tier of an N-tier architecture. And that brings us to the end of our architecture study guide. We've peeled back the layers of data abstraction, mapped out blueprints with schemas versus instances, and explored the physical separation of server tiers to leave you with a final thought to test your new knowledge. Knowing what you know now about scalability in middle tiers, which architecture tier do you think your favorite social media app runs on? Think about it the next time you open your phone. Happy studying!